Good morning, everyone. Today in our calculus, we're going to be looking at Newton's law of cooling, which is our final look at the applications of exponential equations. So this is an exponential equation. Don't let the name Newton's law of cooling fool you into thinking it's anything other than an exponential equation. So all of the techniques that we've been practicing to solve exponential equations are going to be put into good use here. And of course, there's going to be a bit of calculator action. So grab that TI-84 and let's get started over there. So over here we have some stuff about a cauldron, and the cauldron is going to be obviously where our witches brew their potions, keeping with our hit witches and Harry Potter theme here on chapter 7. And that kind of gives us a clue about what we're talking about. With liquids, the way that they cool is not, it's not linear for sure. As time goes on, at the beginning parts, as soon as I usually talk about, when I take my cup of coffee out of the microwave. You can insert whatever other analogy you want there. But when that happens, initially, the temperature of that liquid cools very quickly. And after a certain amount of time, the rate at which the temperature cools starts to decrease. So it really behaves like an exponential decay equation, which is why we're going to be using exponential decay to model this fluid cooling. Now, as that fluid cools, it's got to cool to a certain temperature. It's not just going to keep decreasing in temperature all the way until we get to absolute zero. As we know, that's not really how things are going to work. And further, if you think about the way that the liquid cools, it's never going to cool past whatever the room temperature is. So there is some kind of asymptotic behavior with the room temperature of, wherever our liquid is located. So in a sense, we have to make our room temperature the new zero of our equation. And that's what we're going to see when we look at the actual equation for Newton's law of cooling. So let's read this, and we have, when a material is exposed to surrounding temperature that is lower than itself, the difference between the material's temperature, of course we mean liquid here, and the surrounding temperature decreases at a rate given by, and then we have this nice differential equation. Over here on the left side, this is going to be our dependent variable, and the dependent variable is not, strictly speaking, just the temperature. It's the difference between the temperature and the surrounding temperature, which we're going to call Ts. Over here on the right side, we have our, again, the same thing, our dependent variable, which is still the difference between the temperature of our liquid and the temperature of the surrounding area. So if we look at the temperature minus T surrounding, we can see that this is actually the same thing as a differential equation for exponential growth. Since we know how to solve that already, we can just substitute things here, and we have We have y is equal to a e to the negative kt from our differential equation for a exponential decay. And then when we substitute back for y, we get t minus ts equals a e to the negative kt. Well, what was a then? When we were talking about radioactive decay, A would have been the initial amount of whatever isotope we were talking about. So the initial amount of carbon-14, for example. Well, here we're talking about a temperature differential. T minus Ts is a temperature differential, the difference between any current temperature and the surrounding temperature. So it makes sense that A should be the initial temperature differential. If we keep to our convention for naming things, then T sub 0, or T naught, should be our initial temperature, that making our initial temperature difference equal to T naught minus Ts. And that brings us to our Newton's law of cooling equation right here. This is the solution to the differential equation for Newton's law of cooling. Now there's a couple of things here, or maybe just the one thing here, that kind of doesn't sit too well. I don't know, I don't like it too much, but if you take a look at the way that the constant here is treated, we're enforcing here that k is going to be a negative value. Okay, so unlike before where we said y is equal to a e to the positive kt, this time we're going to be using a negative kt. And again, the only reason I would think that textbooks would want to do that is because you want to enforce or reinforce the fact that we're talking about a negative constant, so there's going to be some kind of decay. So here is the Newton's law of cooling. We've got the differential equation and the general solution. Like always, you don't necessarily have to keep solving this differential equation over and over again, since it is the same differential equation as exponential decay. So generally, people go straight from the differential equation to the general solution. More definition of what is T naught, what is Ts, and then this last line here, and this should kind of make sense, is as the temperature goes to infinity, in other words, as we keep on going with time, as time goes on, the temperature should approach the surrounding temperature. So if I leave my cup of coffee out in the classroom all day long, eventually, at some point, probably around period 2, the temperature of the coffee in my cup is going to be the same as the temperature of the air in my classroom. It's not going to go lower than that. So people see this as some kind of a limit problem. And if you approach it that way, then you might get a little bit crossed up. The correct way to approach this is to just think about this as what happens to the temperature as time approaches infinity. And of course, that goes to temperature of the surrounding. Doing a little bit of solving here, we can see that as the temperature, as the time goes on to infinity, the difference between the temperature of my coffee and the temperature of the air is going to approach 0, meaning the temperature is approaching the air temperature. So that's Newton's law of cooling in a nutshell, and we can do a few things here. I think we just have one example problem and then another problem for you to work on. We'll look at these right now. When placed in a room temperature of 20 degrees Celsius, polyjuice potion brewed at 108 degrees Celsius will cool to 92 degrees after 10 minutes. This right over here serves as our initial condition. Not our initial condition, but, well, yeah, initial condition. And I'll put that in quotes. It's not really initial because this is given to us after 10 minutes. But we needed to have a measurement at some point in order to lock down our equation into a particular solution, or to lock our general solution into a particular solution. What is the temperature of the potion after cooling for 60 minutes in total? So 60 minutes after we take it off of the fire, which is 50 minutes after we measured the temperature. So what is T naught? So the initial temperature of that polyjuice potion was 108 degrees. What is the surrounding temperature? The room temperature is 20 degrees. And after 10 minutes, the temperature is 92 degrees. Okay. So we're going to solve for K, and we should look at the Newton's law of cooling equation. Here's the equation for Newton's law of cooling. When we substitute the initial condition and the initial temperature T naught and the surrounding temperature Ts, T minus 20 equals 88 e to the negative kt. Everything's looking really good. We have a dependent variable, we have an independent variable. Confusingly, they're both t's, so you'll have to make your peace with capital T and lowercase t. But we don't know our value of k. So in order to find our value of k, we're just going to go ahead and use this one right here. Here it is. T10 is 92. And what this says right here is that at 10 minutes after we take our potion off of the fire, the difference between the polyjuice potion and the air temperature is 72 degrees. And the initial difference between the polyjuice potion and the air temperature was 88 degrees. So we're at exponential growth or exponential decay with respect to this temperature difference between the potion and the room temperature. And from here, the solving is kind of routine, kind of what we've done normally. We'll divide both sides by 88. I'm not really going to bother with simplifying that 72 on 88. It doesn't really matter. We'll have a calculator to take care of that for us. Take a natural log of both sides, remembering that the properties of logarithms are such that if I have this power here, I can just move that to the front of the log. This time we are using a natural log. The natural log of e, by definition, is equal to 1, so this enables us to solve this really nicely. We'll just divide both sides by 10. And there we go. We have something nice to put in our calculator to solve for the natural log of k. Or, sorry, we have something nice to put in our calculator to solve for k. Get that calculator out, and yeah, just push enter here, and that gives us a value of k of 0.02. Go ahead and write that down. And here's a warning that I have for you with this calculator business. Now, if you decide to use this number, please don't round it, because that value here, especially with exponential equations, leaving off, just using the first three digits here, 0, 2, 0, that's really going to change your results a lot because of the nature of exponential equations. We're going to be putting this 0.02 into an exponent, so it's going to make a huge difference in our values of our number. So I tend to take that number, and I'll just go ahead and grab that and store it. The store key, of course, is north of the on key, and I like to store that as k. Okay. This way, when I use my calculator and I want to use that value of k, no problem, I'll just go ahead and call up the letter k, and it'll give me the value with no rounding at all. Here on paper, I'm going to write down that k is equal to this number, but I'm not really going to write this number ever again. I'm just going to use the value of k, because now I've told whoever's reading my paper that this is the number that I'm going to use for k from now on. And then from here, we'll just go ahead and substitute and figure out our, what is that, T60? So T60, T at 60, that's equal to 88. Remember, that's the initial temperature differential, or the initial temperature difference. The initial temperature difference multiplied by e to the negative 60k. And we grab our calculator, and we'll put all that in. 88 e, that is an s. Here's an e to the negative 60k. And like I was saying before, you can just type the letter k here now, and your calculator knows to use 0.006, 0.02, 0067, etc., etc. You know the number. So our temperature is 26.398. I'm just in the habit of always writing down the all 5 digits here, and like all the problems that I encourage you to write a sentence here of summary. So the temperature after 60 minutes, it's about 26.398 degrees Celsius. So that is the way to go. Hopefully the solving technique here is okay with you. I am going to show you how to do this a little bit quicker with your calculator. I'm sure you'll be interested in it. So let's grab that calculator again. And I'm going to do this both in the TI-84 Silver Edition, and we'll do it in the Color Edition also, since I don't know which calculators you have. And the magic here is with the solver feature. Solver you'll get from the math menu, and if you scroll all the way down, you'll get to solver. So we'll go ahead and hit that, and here is the equation that I'm going to put into my solver. T, which would be my temperature, minus the surrounding, that's that initial temperature differential here, is equal to, or we can't put equals, so we put a minus sign, noting that I have this parenthesis around the entire left side of the equal sign. T minus Ts minus the right side of the equal sign, O minus S. I have to use O for the original temperature of the potion, since I can't put subscripts here. So I can't put T naught, I can't put TS, so we have to use a letter. That's the way TI calculators work. So O minus S, e to the negative k, and I can't use T again because I've already used T for temperature. So I'm going to use X over here. And when I scroll down, that gives me the equation up at top, and then all of these places to put values for constants. And I'm going to do this. This is where you need to be with the TI-84 Silver, and in the TI-84 Color. Similar, it just looks a lot nicer, of course. E1 is the left side, E2 is the right side. I'm using the same values or the same variables here. T, S, O, K, and X. And this time when I scroll, and if it would let me scroll, that'd be nice. There we go. I'm going to substitute all of the values that I know. So let's pretend I didn't know what the value of K was. And as you can see, this value of K is incorrect. So after 10 minutes, the temperature was, 92? The surrounding temperature is 20 degrees. The original temperature was 108. I don't know K, but this all happened at X equals 10. So I'm going to put my cursor now on K. This is exactly what you would do in the Silver Edition as well. And then I'm going to push alpha, enter, to solve, and the calculator will go ahead and give me that value there. Now the advantage of doing it this way is, number one, it's a lot easier. Number two, you get a view of all of the constants or all of the variables in one view. So that is really nice for us. Now the next one answer would be, what would the temperature be after 60 minutes? So now we're going to change x to 60 because that's our time. K is going to be the same, O is the same, S is the same, but T is going to change because as a consequence of us changing X. Same routine, alpha, enter, and that gives us 46. Wow, that's a little bit different than the answer that I got before. I'm wondering what happened here. I'll investigate that in a second. But, you know, I actually trust this 46 a heck of a lot more than I trusted the previous answer that I got. So let me take a minute to see what happened. Okay, so silly me, I forgot that I needed to add 20 to this. So if we take a look at that 26 here, and we go back here to our equation, I'll show you where the mistake was. My mistake. Right over here, I forgot my plus 20. Wow! Mistakes happen, of course, and I feel foolish, but at least I got to catch it using my calculator. So, yeah, 46.398. That's the answer that we should get. And here in the calculator, again, that was a whole lot easier to do. If you have the color, I highly recommend getting the color version or upgrading. If you have the means to upgrade to the color edition, it does look a lot nicer. Getting back to the work, this kind of leads us to the question, well, how much work do I need to show? Since I can do it all on the calculator, you know, why do I need to bother writing all of this? And of course, this is an academic math course, so you do need to show some mastery of the equations and your ability to solve them. So depending on whoever's teaching you, you can either have to show all of this work. Some teachers say you just need to show the equations, and then we know you have a solver, so use it. I'm personally of the opinion that if I'm going to give you a calculator to use on your test, use your calculator and don't make any silly algebra mistakes like I did here. Okay, I would have caught myself, you know, or I would have produced my own error, even though I know the material reasonably well. I would think, even though I know the material reasonably well, I would have created what amounts to an algebra error, even though I had the calculator in front of me, which is kind of an unforgivable thing. You don't want to have algebra errors if the calculator is sitting in front of you. So if you're in my class, you really only need to write down the equations with the numbers substituted in it, and then use your calculator to get to the solution. Okay. All the other solving stuff, not so necessary. I don't need to see you solve it unless, of course, you have no calculator. So the blue stuff, that's what I expect you to show in my class, at the very least. If you want to impress me, go ahead and do the rest of it. From here, we should take a look at some important ideas. Nothing that we haven't discussed before. Here is our equations. This is a differential equation leading directly to our general solution. As a well-known differential equation, you don't really need to show any integration. And of course, use your calculator solver for the unknown, which is what we're going to do now, since this is running a little bit longer than I thought it would. We have a hard-boiled egg at 98 degrees, and we're putting it into a pan under running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is 38 degrees. How much longer, and I'm going to highlight that because that's important, it's even in bold. How much longer will it take for the egg to reach 20 degrees Celsius? So let's put our equation together. First of all, we'll write down the things we know. The original temperature of the egg is 98 degrees. The surrounding temperature, it's not really the air temperature anymore, it's a water temperature in the pan, that's 18 degrees. And T, the temperature after 5 minutes, that's going to be equal to, what is that, 38 degrees? Okay. Write down those things, and next we're going to write down Newton's law of cooling with all of our variables substituted in it. So T minus Ts equals T naught minus Ts, e to the negative kt. So the temperature minus 18, that's going to be equal to the 98 degrees minus 18, e to the negative kt. And if you would like to simplify that, that's fine as well. T minus 18 equals the 80 e to the negative kt. So that is our particular solution, but we don't have a value of k yet, so we're going to use this to help us out. So T5 minus 18 is equal to 80 e to the negative 5k, and that's going to be equal to, what is that, 38 minus 18? And then we'll go ahead and grab our solver and solve that out. Okay, our temperature after 5 minutes was 38 degrees. Our surrounding temperature, that's 18 degrees. The original temperature of the egg was 98 degrees. We don't have a value of k, but we know that temperature after 5 minutes was 38 degrees. So let's go ahead and solve for k. Our value of k is 0.27725, which we'll write on our paper now. Here we go. K equals 0.27755. It's 27725. The next equation we're going to set up is, when will the temperature be 20 degrees? So I'll put a 20 here. 20 minus 18, so I don't make that same mistake that I just did. That's going to be equal to 80 e to the negative kt. Taking a note that k is actually not unknown. K is this value over here. And then we'll grab our solver and solve that out. This time we know that the temperature is 20 degrees. Surrounding temperature is still 18. The original temperature is still 98. K is still 0.22277. And now we're going to solve for x alpha. Solve. That gives us 13,304. And now we get to answer the question with a summary, and notice in blue it says how much longer. So if it took a total of 13 minutes, then it's going to be eight more minutes in order to get to that 20 degree temperature. So in 8.304 more minutes, the temperature of the egg will be 20 degrees. So that's it for our solving here with the Newton's law of cooling. Hopefully that was helpful to you, and we'll see you on the next time. Have a good day, everyone.